Hello and welcome to my YouTube video. In this video I'll be explaining a theory that is based on Einstein's famous theory of relativity. This theory is based on the definition of time, which is given that a measure of how long it takes for light to travel from point A to B, given A and B have a distance between each other. In this case, time is not an instance, but is the measure that determines how long it took for light to reach point B from point A, given that the light began exactly at point A. Light is always constant, or the speed of light, that is, based on this theory. In this case, then, light does not slow down or speed up, but it actually bends due to gravitational pull. I'll be explaining this in this theory as well. The speed of light may appear as if it was different in different parts of the universe depending on how much gravity is on a certain part or location in the space-time blanket. This can be visualized using a golf ball analogy. If you were to have a golf ball go straight without any force acting upon it, besides gravity, which in this case would not slow down the golf ball, making it go at a constant speed, and if there was a curvature that went downwards and then upwards, and if the golf ball followed the path concerning there is gravity, you notice the golf ball's speed increases as it goes down the slope. Now, once it goes up the curvature and the level is the same as the previous straight ground, you notice the speed of the golf ball will be the same as it were when it first began. This exactly visualizes how the space-time blanket works, and light as well. Now, some people may be confused about whether gravitational pull speeds up time or slows it down. In this case, it speeds it up. This can be explained with the definition of time in this theory. When there is no gravitational pull within the location of the space-time blanket, the distance of A and B is bigger than when there is gravitational pull, because when there is gravitational pull, it is almost like A and B are pulled together. Now, you may be asking, how can we determine the exact measurement of how long it takes for light to get from point A to point B? Well, this can be calculated with the equation, which is the barycentric time constant equation, which is the time constant of an area of space-time is equal to the square root of the gravitational acceleration multiplied by the difference of pi divided by 2 minus 1 multiplied by the speed of light multiplied by 10 to the negative 10th. And then this whole square root divided by the gravitational acceleration multiplied by 10 to the second. And this whole thing subtracted by 1, and then multiply this whole by 10 to the negative second, which gets you approximately, if you use Earth's gravitational acceleration, 0.03176 approximately. There is also a simple equation which requires that you know the variable of p. This equation is the time constant is equal to the gravitational acceleration multiplied by the difference of pi divided by 2 minus 1 divided by the variable of p. Now, what is p equal to exactly? Now, if you know the time constant, which can be found with the previous equation, you could easily find the variable of p. P, in this instance, is equal to the gravitational acceleration times the difference pi divided by 2 minus 1 divided by the time constant. Here's an interesting fact. Pi divided by 2 is equal to the variable p divided by the gravitational acceleration times the time constant plus 1. Many have asked the question which has to do with how black holes works with this theory. So, how does this theory work with a black hole if the time is equal to 0 in a black hole, but the gravitational pull is really large? Well, there is one simple answer. Light does not exist in a black hole, so there is no way for light to reach point B from point A, which means it takes 0 time to get from point A to point B. Thank you for watching this video. I hope you learned a few things and may consider differently how light works. If you have any questions or want to comment on my video, you can comment below.